Bill Berner Physics Demo Show. My name is Peter Harnish. I run the instructional labs here for the Department of Physics. I am not doing this alone. We also have...
Oh, Mary Markapole. I am taking over the lecture demonstration lab.
And...
Bill Berner, I'm giving up the lecture demonstration lab.
The Bill Berner. The Bill Berner.
So, we are here at UPenn. There are many things that could be said about UPenn. We have a long history. Founded by Benjamin Franklin, we're the oldest university. We're older than this country, all that kind of stuff. But like most people, I know a lot more about my backyard than I do everywhere else. So, this is the intersection of 33rd and Walnut, which I feel is probably one of the most important intersections in the city. You entered the David Rittenhouse lab there. That's that big door. If you cross 33rd, you get to the Moore School of Electrical Engineering. In 1946, they built a thing called ENIAC, which was the first universal computer. What that means is it was the first computer that could run any program you give it, not just the one program it was built to do. This computer was so amazing, so inventful, so powerful, that it was thought there were only going to need to be 7 of them ever created, because you could go to the one on your continent and do everything you needed to do. To show how impressive this computer was, how efficient, it only cost half a car per hour in electricity to run. It was so fast that your iPod is only 1,000,000 times faster than this computer. And it had so much memory that it would only take 140,000 of them to store one MP3. Now that is not me disparaging ENIAC. That is showing you how fast and how far we have come with computers. That this was thought to be the only computer we would ever need when it was built. And it can't do any of the things that the computer in your pocket can do. Now, if instead we cross Walnut, we get to the laboratory for the research on the structure of matter. This was Penn's brilliant idea that if we make physicists and chemists and engineers and mathematicians all live together, they might have to work together and produce interesting things. And indeed they have, including in 2000. The Nobel Prize in Chemistry went to the development of electrically conductive polymers. That's plastics that behave like metals in the right situation. 2 of those scientists worked in LRSM from our physics and chemistry departments. I'd also like to point out that this work was published in 1975 and it got the Nobel Prize in 2000, because the Nobel Prizes are only given for things that are so great, it usually takes a number of decades to prove that they were good enough. And lastly, of this corner, because it's the one that I know the most of, my own home, the David Rittenhouse Laboratory. 1/2 of the 2002 Nobel Prizes can be split up, went to the understanding of cosmic neutrinos. Effectively what this means is that our own Ray Davis built a giant machine under the ground, and it should have collected something like 12 atoms a month, and it collected 4, and everyone went, Ray, your machine's broken. He went, no, you need to reinvent how stars work. And it turns out Ray is the one who was right in that argument, and they gave him a Nobel Prize for it. Also, some of you may have heard of CERN. It is a giant particle detector in Europe. It is the largest machine ever built. You may have heard of CERN because it discovered things called the Higgs boson, which redefined how mass works. The Higgs boson was detected by the Atlas detector, which the hardware for was designed 200 feet that way. On this floor, about 200 feet that way, Atlas was designed. All the hardware was worked up by our own physicists and engineers. And maybe most recently, the 2019 Breakthrough Prize in Fundamental Physics went to Jean Malie and Charles Kane for their invention of topological insulators, which are a thing so impressive, we really don't know what they could do. But if a quantum computer is ever built, the good odds are that it's going to be built using topological insulators. probably most importantly, the best thing to have ever come out of DRL is Mr. Bill Berner. Bill has been doing this demo show for over 20 years. He's been teaching for almost his entire life. And I am willing to bet that probably the best thing to ever come out of DRL are going to be students that were influenced by Bill.
Thank you for coming. So this is really a neat thing. When we first started this, part of what I was doing, I had taught for a while. I've now got a room full of all the stuff I wished I had when I taught, but I was just handing it over to other people who taught. So this was an excuse for me to actually show this stuff to people. So I'm excited to have that opportunity once again. All right, who thinks they can hit this bulb with a balled up piece of paper? No, you can't do it from back there. Now, anybody up here? I'll bet you could try. And, wait, the theoreticians are so clever. I'll bet you he can.
Can you ball up that piece of paper?
So ball that paper up. Don't throw it yet. Okay? I can tell. Okay. So, all right, so let's pay attention now. Let's see how good these people are. Okay? All right, so let's throw those balls of paper at that light. Whoa. Okay. Pretty sad performance. But in fact, let's think more seriously about this. It actually wasn't bad at all. It was pretty amazing, really. Because although there really were some kind of embarrassingly wide swings here, they really weren't. Look at how many places it could have gone. Not one of those pieces of paper came over here. Great job. None of them went up there. Just about all of them came within a zone about this big. Okay? And how did they do that? How did they possibly do that? Now, it turns out that we discovered, as little kids and as a civilization, that light travels in straight lines. In other words, if we look at something, that thing is at the other end of our line of sight. And so direction is easy. You could pretty much get an idea of what direction to throw that in just by where the bulb was. But distance is pretty tough, because that line of sight just keeps going forever. And so the other thing that most of these people didn't do is they didn't land back here. They didn't land up here. They actually did a pretty good job of getting within the length of the position of this thing. And so that's really what we want to have a look at. How does that happen? So if we were to, can I get a board? So this light bulb is sending out an infinite number of rays. At least I'm going to say that, and you're going to believe me because I'm the gray-haired guy in the front of the room, and you always believe the gray-haired guy in the front of the room, right? But we can kind of prove that. You say, well, maybe there's just one ray, and it's coming right to my eye, and nobody else is getting it, okay? But if I move the bulb around, now apparently there were rays coming out the side and the front, okay? So my diagram's not bad, all right? And so let's put an observer in the picture.
That's an eyeball, for those of you
That's
that can't tell.
but for those of you who have a tough time with my drawing, look at this. We've got an eyeball, okay? All right? So now there is the physics eye looking down this line and saying, I want to throw my paper that way. Okay? But that doesn't tell you where it is. In fact, this ends up being the astronomer's problem. Because astronomers have a telescope, they point it at a star, and they say that star is right out there, but they have no idea how far away it is. And for thousands and thousands of years, they couldn't tell the difference between planets that were pretty close and stars that were really, really far away. And so planet was the Greek word for wanderer because they thought they were the same thing as stars except they moved around. But in fact, they were quite different. So, how do we solve it? You did a much better job locating this light than astronomers did locating planets. Well, what you do was really clever. You guys are you're grand. You came in with two eyes. What a good idea, okay? Because now this other light ray coming to this other eye gives us two reports. The lines are not parallel, and we can trace back and get a sense of where things come together. Where is one point in space that could be the source of two different rays? We call this binocular vision, and it is critical to the ability of organisms to locate things. Because light always travels in straight lines, and we can count on this happening, right? Wrong. I've asked you to take on faith the fact that light rays emerge from this in all directions, but because there are so many rays, we can't keep track of them. In recent years, we have been provided with the star shower for folks too lazy to climb all over the front of their house and hang lights. And so you just shoot this thing at your house and it's Christmas, right? So what we've got, though, is a single point that sends rays out. So just like my green light, we've got this, and if we turn the lights out, we could say, there they are, pretty zoomy, but you know, that, we still can't see them, right? We would like to see what the light is doing. You can't see light sideways. Now we're cooking. So this actually looks like the diagram I had on the board. It just gets better and better, doesn't it? Right? Okay. So now if I take my eyeballs, it's pretty believable that these eyes could catch a pair of those rays and say that's where it's coming from, right? We've now got a sense of how we see things. It turns out that we've got good evidence that light does travel in the straight lines of which we spoke. We've now also got a way to get information of not just direction, but position. We call this binocular vision. Okay, it's of tremendous importance. I hope you kind of understand that only when the object is relatively close compared to the distance separating our receivers does that triangulation work. We also have the benefit of focusing our eye, and the effort of focusing is another input we have in determining how far away things are. But let's take a look at the use of binocular vision. We have here what I hoped was going to be a really good picture of an eagle, except this sucker's cross-eyed. Right. National Geographic's not going to buy this picture from me. Okay, we got a cross-eyed eagle. What's going on? He's using binocular vision. If you bring something in closely, you know that your eyes come together. Little kids learn to walk before they learn to use binocular vision, and they walk into walls. After a few tries, they begin to realize just about the time they're going cross-eyed, they're getting smacked in the face. Okay? And so they start to put their hand up and they begin to calibrate this system. So an eagle is a predator. An eagle depends on catching evasive little critters for breakfast, lunch, and dinner, and you pretty much only get one shot at that mouse. You better locate him pretty well. On the other hand, if you are not a predator, so you've got now, yes, a cutesy little hummingbird. Okay? What do hummingbirds eat? They don't eat eagles, right? Okay? Notice that beak. Hummingbirds suck the nectar out of flowers. Flowers are not a terribly evasive organism. Let's say you come in on that flower and miss the first time. You know what? You get a second shot. Okay? So the hummingbird does not need his eyes for accurate location. But it turns out there are a number of creatures that would like to eat a hummingbird. Hummingbirds need to protect themselves from being snuck up on. So they say, you know, it's kind of nice having both eyes here, but I got no idea what's going on back there. If I could just move each eye to one side of my head, this guy could cover half the world, and this guy could cover half the world, and nobody would sneak up on him. And so now when we take a look at animals, the placement of their eye is a pretty good indicator of what they need to stay alive. Okay, and so that binocular vision is an important way that we locate things, and it's important for us to understand how we use it to locate things. And so now, we think we've got this wired. We understand the rules. Light travels in straight lines. We can always count on that being true. We can find the source by simply looking in the direction that the stimulus came from, right? Just like when you walk down the hallway in your school and that annoying guy walks next to you, reaches around and taps you on the far shoulder. Right. And you look over on the wrong side and everybody laughs at you for getting burned, right? So what just happened? Well, what happened was the stimulus didn't come from the source. And now if you go to a really annoying school, maybe that happens so often that you develop the habit of actually looking left when somebody taps your right shoulder. And you go out into the real world.
Everybody's looking for one particular kid right now.
You go out into the real world with this really bad reflex of looking the wrong way. Well, when it comes to light, that annoying student is a mirror. Because now we can have light starting out on its straight line path, but then ending up not doing that. It's over here. And so what's happening? We are bouncing that light. Okay? And so that light that starts out going one way ends up going another way. So what happens? If we bring our eyeball into the picture, our eyeball catches a light ray, our other eyeball catches another light ray. We do the same job of saying, well, where did that come from? We come down, they haven't come together yet at the mirror. They bounced off the mirror this far apart. So what does our eye do? It keeps tracing and says, I think it came from behind the mirror. Could that possibly happen? Now we're going to do this. That's right. This is the way you hypnotize a group of students. Because they look in there and they say, wow, look at those good-looking people. But those good-looking people appear to be behind this mirror because of that behavior. Because the light scattered off the mirror, you continue. So you're being just as burned by this mirror as you were burned by that pain-in-the-ass student who tapped you on the shoulder. Okay? So what's going on here? Well, we're on the inside. This is our building. And this was a falcon. And this is the way many birds meet their end, okay? Because windows are very reflective, and you get to work on this gradually. You know, you annoy your parents as a young child by walking into mirrors and smudging them. but you don't fly into mirrors. You get to work out mirrors before you can go fast enough to hurt yourself, okay? But birds get one shot. That was on our window for quite a while till we got window washers up to remove that, okay? But we're smarter than that, right? I mean, we wouldn't get fooled. Well, let's see. Oh, right, we want this guy.
Wow!
So, see, when we have a group this big and they're all annoying and talking and I'm thinking, oh, this is terrible, nobody's paying attention. I can get back here and see the world through rose-colored glasses and it's all better. Okay? So what we've got here is a simulation of a one-way mirror, which is fake science. There are no one-way mirrors. There are partially silvered mirrors. So let's imagine a mirror that only reflects half the light. That means it transmits the other half. So if we put something in front of that mirror, we can kind of see the reflection. But it's not very bright because only half of it's bouncing. But let's get a lot of light in front. And now that works pretty well. We can kind of see a reflection. We can do the same thing back here. Half of this is reflecting, and so Peter is having a grand time looking at the reflection of this, but you're also looking at the transmission. And so when we talk about a one-way mirror, we're actually talking about an imbalance caused by the way we light the place. So if we're on a dark side of this, not much light comes through and you see yourself. But if we light the back and darken your room, then you see through it, okay? Or you see the reflection. So why are we doing such a thing? Well, please notice, one of the problems with all of this is that everybody would have to be in the right place to see it. We're using the miracle of digital photography to get everybody's viewpoint to be in the right place. And so consequently, you can now see the object and its reflection somewhere back in here, okay? So where is that reflection? We need another of these incredibly expensive devices, okay, which are vinegar bottles with the bottoms cut out. So look at this. I can put this guy back here and we can move it around until it's actually, and what this needs. Yeah. And so now we've got the real object sitting on top of the reflection. So you're seeing a real object through here in the same place that you're seeing the reflection. So how do they line up? Remember, Lewis Carroll talked about through the looking glass, that there was a world that seemed to exist back here. Is it really acting like it's on the other side? Well, now, if only we could get everybody to look down on top and see. We could turn this around and you could see, or we could give you an overhead viewpoint. Look at that. How did they do that? That's unbelievable. Okay, so now we're here, okay? And I'm cleverly staying off camera so you can't see how much hair I've lost. But you can now see where the object is right here and where the image appears. And so these things are, the image is just as far behind the mirror as the object is in front. It really does give us the impression that you can go through the looking glass, that there's a world on the other side of the looking glass. Lewis Carroll wrote his, after Alice in Wonderland, wrote the book Through the Looking Glass because things look that way. Architecturally, this is used to make rooms look bigger. But as I say, we're too smart to get fooled by that, right? We kind of know. So a virtual image is the right side up image in a flat mirror that is caused Okay, and so we've now got almost a whole class through the looking glass. We've got a world back there. These are used architecturally to make small rooms feel bigger. But the question is, can we really convince you that there is something real on the other side? Could we be as fooled as that bird was? Now this is after a lot of research. We started out with a 40-inch high mirror. That was really uncomfortable. Okay, so we went down to a 30-inch mirror, and this is much better, much better. It looks like I've got two legs on the ground, but you really can't see my left leg, right? You can only see my right leg and the reflection of my right leg. The reflection of my right leg looks just like my left leg, and more importantly, the reflection of my right leg is in the place where you want my left leg to be. So it pretty much looks as if you're seeing an undisturbed view of me standing here. Okay, no big thing, right? All right. But with this optical illusion, I can break a number of laws of physics. I can break Newton's third law. I can lift myself up by my bootstraps. Right? Do you know where that term came from, bootstrap? In the old days, before we had a wimpy society, yeah, you wimpy people born after 2000 who are too weak to put your damn boots on. So there's a zipper down the back of your boots, you wimps. In the old days, boots were like a solid hunk of leather. They had two things on the top, and you pulled like crazy to get your feet into them because they were barely as wide as your foot. They were bootstraps, and it was always suggested that you could grab your bootstraps and pull hard and lift your feet off the ground, which is what your computer does every time it starts up. It lifts itself up by its bootstraps. Now, you students of Newton's third law know this is impossible, right? Unless we bring in a flat mirror and a virtual image. Because I got to lift myself up, right? I mean, this is hard. This is about, I won't be able to do this for another year. This is about the last time I can lift myself off the floor. Because it's... and I don't even know if Mary's strong. I don't know. Okay. It's hard to stay in the air while I turn. And so you have been fooled. That bird was no dumber than you. You would fly right through here, right? Because this is such a believable thing. In fact, you would hire me for the NBA because look at the hang time. Okay? So, now clearly I'm standing on the foot you can't see. All the light from this leg is being used to fool you into thinking you're seeing two legs. Okay? So this is a pretty believable illusion. Your binocular vision places that reflection where you want it to be. We call this a virtual image. The critical issue in virtual, right, and us physicists had virtual before you gamers did, okay, is that it only seems as if it's there. Your eye traces back, and when you get to the mirror, the lines haven't come together yet, and so you need to go behind the mirror for that converging point. So now you're going to say, I see that thing on the other side of the mirror. We call that a virtual image. There will be times when the converging point is in front. We're going to talk about that later. But right now, we've got virtual images.
Bill's talked to you about plane mirrors. And plane mirrors are awesome because you can pop your pimples and you can fix your hair. Right? And those are kind of important things in the morning, even well into your adulthood. And that's great. But, who do you see in this mirror? Never mind. Who do you see in this mirror? Wow. That was great. No, nobody?
You got it, guys. You can achieve it.
This is not actually a multiple choice question. It's not a hard one.
What? It's not you. What is it? Why didn't it think so?
There we go. Ibrahim sees himself. But now, who do you see in this mirror? Ibrahim. Yeah. You see Ibrahim, not yourself. Because this mirror needs to be aimed at you for you to see yourself. This mirror needs to be aimed at you for you to see yourself. What if there was a way for us to be able to get an image back to ourselves without us having to necessarily be, repositioning ourselves to be in front of the mirror all the time? What if there was a way that we could get a signal back from almost any angle? We're sponsored by Wawa. I'd like for you to know. And in your spare time, if you have extra Wawa crates and plain mirrors, you could do this with it and make a retro reflector. And so now, everybody can see themselves now, right? Even in the back of the room, you can see yourself now, right? Oh my God, I did not spend enough time in front of the mirror this morning, right? This, in fact, is such a useful thing that we went ahead and put one of these up on the moon. So this is a retro reflector similar to the one that we have up on the moon. It is a piece of glass that has 3 reflectors oriented at right angles at the back of it. So if you look at it in profile, you can see that point. And Pete and I have a high level of trust in each other. So Pete is going to let me aim a laser at his head. Right? We're not at trust level arrow shooting yet. We're not going to do that. But I'm going to take this laser and I'm going to aim it at the retro reflector on top of Pete's head. And you guys are all going to look at Pete, but look, the interesting thing is back here on my terrible Captain America shield. You see it come back to the box? Right? And if I move across the room, Pete doesn't have to move. If I move across the room, it happens again. It comes right on back to the box. So you can see every time I hit that retro reflector. I do not have to steady his hands. I would not recommend myself for brain surgery. I would not want me operating on your brain unless you want to be lobotomized. But no matter where I am in the room, this comes back to me. And why is that? Well, let's take a look at the way the light is bouncing here. If I shine this laser onto this reflector, you can see it bounce off the bottom mirror, hit the side mirror, and come back up. Right? Now let me get it so that I can hit all 3. And now can you see it coming back along the plane that I'm aiming the laser? Even coming back towards me? Can you guys see that it's heading back in that same direction that it came from? I gotta get it the right angle. Alright, so you guys are seeing that? That's amazing! So, 1 mirror is great for fixing your hair. 3 mirrors is great for being able to fix your hair from any angle. What could we do if we had a ton more mirrors? Right? And so we know that triangle has 3 sides, a square has 4, a hexagon has how many? 6, and an octagon has 8. Right, that's awesome. And a icosahedron? It's okay. It's okay. But no, because it's icosahedron, I think it's like 22 or 24 or something like that. I don't know. I have to look it up. All right. So what do I have here? I have a piece of flexible eyeball. Right. It makes this cool sound, which makes me happy. But what's neat about it is that I can also curve it. How many sides does a circle have?
1 very long.
Or infinitely many. Right? Right? And so if I curve this, I can have infinitely many reflectors. Okay, and let's take a look at what that does. Okay, so I'm going to aim this in this direction, but I'm going to then project it back up on the board or on the screen. And you can see lots of dots, and that's exciting when it's plain, right? But then I can start to curve it in. in multiple directions. And all kinds of interesting things happen. So I feel like we need to take the time to really take a look at what's going on with a curved reflector. Everybody's favorite conic section, a parabola. So this is a parabolic reflector, and if I hold this up, what do you see? Everybody excitedly sees themselves, right? But upside down. You're upside down now. There's something different and strange about this mirror, right? And if I were to bring out a camera, oh, look at that camera. Now I'm going to back up, and I'm going to try to keep it in there. Keep it in my mirror. Back up, back up, back up. I'm not so steady as I used to be. Oh, I lost it. Hey. And this is the view that you were seeing, was the upside down view, right? And then I can come back in. Whoop, something weird happens and I can't keep it there, and then there it is again, staring at it. Something happens in this range where I go from right side up and magnified to upside down and smaller. That is some special space for this mirror. I know, everybody's complaining. I'm going to cough to death. These are basically liquefied cough drops. This is cough syrup being sprayed at you. So, you know, you're not going to die from this. You're feeling a little greasy out there. All right. So let's get this lines are crossing each other now. What happens with Bill and the plane mirror is different. Now these lines are crossing each other, almost at an intersection. This is what we would call a focusing point. Right? If you didn't love a parabola before, you know you love it. Your first child is going to be named Constant X Squared, right? Fun fact, I did actually accidentally meet one of my kids later when he died.
What? You can't just say that. You gotta accident.
Her name is Ellie, and her middle initial is starts with a D. So her middle name starts with a D, so her name is LED Honda. And so I accidentally named my child Light Emitting Diode. So we have another mirror here, just like the one that I just showed you. Yeah. What we were taking a look at before, where all those lines were converging, is a focusing point, where we could take light from infinitely far away and it would come to a focusing point. You've probably seen people do this with curved mirrors before, or even with lenses, where they try to light ants on fire, right? That's one of the first signs that you're going to grow up to become a serial killer. So you know, that's like cruelty to animals. It's not okay. Or bugs. All right, so I'm going to take this thing, and I'm going to aim this at all of you guys, and I want you guys to tell me how many bulbs you see. At some point, more than likely, most of you saw two. Those of you that are up in the rafters probably didn't always see two or didn't manage to get to see two. But so fortunately, we have this big old fancy eyeball that we can put in place for you, right? And now you can see two light bulbs for sure up on the screen, and they look super convincing, don't they? Right? But like, one of them's not real, right? And so this light bulb's real, and it's warm, and gosh, I'm so cold. But this one is not real, and we know that this is some kind of a reflection. We can bring in other objects, and they're coming in from the wrong side. So you guys can see me coming in from this side, but the light bulb is coming in on the top from the other side in the mirror, right? And so what is happening here is we're actually making a real image, not a virtual image. We saw with the plane mirrors that Bill used that light did not make it to the back side of the mirror. What we saw with this curved mirror was that light stayed in front of the mirror and came back together again. So light is coming from this light bulb, reflecting off of this mirror and coming back together again here. This is at the radius of curvature of this thing, right? Anything that has a curve to it has some kind of radius that can be measured, that we could fit a circle in there or a sphere in there. It would have a radius. So this is not at the focus, but at the radius of curvature for that. So this is a very real image, and we can do very real things with this. Can you imagine if we could take, say, a signal and send it out to a curved reflector, and then we could take that curved reflector signal and send it back to something else? Could we do something useful? And I think that thing would be direct TV. I do. Right, and so what have we set up here? We've set up 2 more curved reflectors, and we can do this with light. We can do this with any kind of wave and energy. So what I have here is a heat lamp. I know that it's heating up because I can feel the warmth on my freezing cold hands. Some of you are going to start to see it red hot. Some of you will see it on the screen come up and start to look kind of purpley on the camera. So it is sending off heat and energy and light in all different directions. This is sending off light in the infrared spectrum, so, you know, less than red. And it's reflecting off of this curved mirror, and it is sending a signal all the way down to this curved mirror, and then it's going to focus it right in this area. And this is what your satellite dishes do. You have a signal that's coming from some television station that's going out into space, hitting a curved reflector, and then getting sent back to a dish that's on somebody's house that has some little receiver sitting right exactly in the focusing space of that reflector and sending that signal into your home. So how can I prove that this is actually happening? Like, oh, look, that's it, it's happening. Believe me, I can feel heat here, everybody go home. Right? That show's over. No, that's not how it works. We have here flash paper that lights fire at like low temperatures. And so it lights fire really easily. And I can bring it close to this light bulb that I can tell is really warm because it's burning my fingernail when I get too close. And it doesn't catch fire. So, well, that's crappy flash paper. And can I turn down the lights a little bit? Okay. Sorry. So what I can do, though, is I can bring this flash paper into an area where I can focus the bulb. Oh, wow. Yeah. That's not a joke. Fun fact, I'm terrified of fire. Had a couple really bad burns when I was a kid. Left me pretty terrified. But if I'm going to do the job, I'm going to do the job. Right? If I'm going to replace Bill, I'm going to have to get electrocuted and catch fire.
We're going to jump straight to the more fun version of bending light, prism.
And in the case of a prism, we've got a double transition. We're going from air into the prism. We pass through the prism, and then we're going from the prism back into the air. And so if I fire this guy across the room, you can see it's a straight line. We are using a gadget from a laser level to take this point and smear it out to be a horizontal line, which lets us keep track of it a little better. And so if I put this here and bring the prism up, it hits the prism, and look at that. We chopped the light out, and what did we do? We redirected it. It's now bent downward, and here's where the wide beam is helpful, because the back of this prism is frosted white, so we can see what takes place, and we see that the laser bends down to horizontal.
Don't look at the wall, look at the prism.
Look at the prism. It's gone horizontal, and it exits and bends a little more and comes down and hits the door. So this prism is changing the way the light moves. This is a new way to fool you with light. Remember the old way we bounced it? Now we're bending it. So all that works just fine, but sometimes our first study of something is a super simplification. And that simplification here is we have one color. Lasers work really well because they're only dealing with one kind of light. Once again, if we go back to that wonderful time in history when boots didn't have zippers, we also had carousel projectors. For you physics teachers, this is a great source of really full spectrum white light. So if we fire the light into this glass crystal, it changes path as the camera shows. So the light starts out headed this way, ends up bending, but something really surprising happens. It turns from white light over here into Roy G. Biv, right? Red, orange, green, red, orange, yellow, green, blue, indigo, violet, right? We have a full spectrum. Now this was known in the Middle Ages when kings of France put wild chandeliers in their palaces. Light would hit the chandelier, they would get rainbows on the wall. The explanation was that this pure, perfect white light was being polluted by impurities in the glass that led to colors. So 1600s come along, Isaac Newton steps in and he says, no, I think that what's happening is we're breaking white light up into colors that were always there. That white light, in fact, isn't pure, it's actually a combination. So this is kind of a philosophical debate. Both ideas make sense. Both ideas are well reasoned. But the question is, can we resolve it? Is this a scientific debate? Is there a difference that we can observe that would let us choose one idea over the other? And so Newton comes in with a really super idea. He is, in essence, a scientific superhero. And if you want to be a superhero, you've got to change into your superhero outfit. And so now Newton suggests that if we take another prism and put it into the beam, if it's impurities in the prism, we should end up with more intense colors. But if we're clever and we take this prism and flip it over, so that now we're going to get the light to bend the other way, so that now the blue light that's down on the bottom bends further, comes around and crashes back into the red light. What we end up with is the back side of the album cover. That's right. And on the back of the album, they take the colored light and run it back through a prism the other way, because we now know that the red light bends less, the blue light bends more. And so we've now got this behavior if Newton is right. Can we reconstitute this spectrum? And so we take our second prism, and we're bending that way, so we're going to bend this way. No, we're going to bend this way. And so now what comes in here is a spectrum, right? We can see that color. And what comes out of here, and let's get these guys to join back up, and we do that just by blending. And we're back to white light. And so we've done here with these prisms exactly what Pink Floyd did with their album cover. And let's get this guy. There's our white light right there. Okay? And what Isaac Newton did with his demonstration. And so this really shut down the critics. This is very good science. So now the hypothesis that we analyze or break light up with the first prism and we synthesize or reconstruct light with the second prism is demonstrated. We've used observation to resolve this debate. Okay, and that really is at the heart of why science has become one of the best ways we have of knowing things.
All right. So far, we have talked about light and how to get light to not travel in a straight line by it reflecting off of things. There is another famous way to get light to not travel in straight lines, and that is to get light to bend. So this next set of things we're talking about is the idea of getting light to bend. Now, if we just have lasers, right, and we throw that up, it's going to be a straight line. It's a straight line. It's always a straight line because it's light. It's traveling in a straight line. But, very importantly, that demonstration was just performed only in air, right? In this tank, the top half of this tank is just air. The bottom half of this tank is water. Right? So if we take our laser and we put it in, we can see that light travels in a straight line because I'm just talking to talk. Right? No. Very carefully, we've noticed here that we are traveling straight at the wall. Right? That interface, we're going straight at it. If we come at it from an angle, right, we can see there's some angle of the light coming in, but it doesn't keep going in a straight line. It bends down, right? So at that interface between the air and the water, the light is changing direction, right? And if we choose other angles to come in at, we will notice the angle out also changes, but it changes by a different amount depending on that incoming angle. If you've ever put a straw in a glass and it looks kind of funny when you put it in, or if you look down at your legs while you're in a pool and they look odd or at a funny angle, that's because your face is in air and the object you're looking at is in the liquid. And the light is doing things between the two, which can cause that image to change.
When we watch a laser beam go from air through the surface of water and into the water, our first thought is it's a line. It's got no physical dimension. It just goes in all at once. But in fact, it's a tube. It's not terribly big, but it's got a width. And as it enters, that tube enters in such a way that the bottom side hits the water before the top side. And there's a moment when part of that tube of light is in the water and part of it's in air. In other words, the whole tube isn't doing the same thing. This is a transition that leads us to wonder whether or not a speed change from one to the other might be the source of the direction change. And so what we'd like to do then is see if we can model that. So we've taken not just a single wheel, but two wheels. And we've taken two different mediums. The floor, which you can see here, right? The top of my head, not one of the mediums. But if we take this and roll it on the floor, both wheels have the same experience and it moves in a straight line. But now, at great expense, we've fished through a dumpster and gotten scraps of carpet. Okay? Wheels don't roll as well on carpet as they do on hard cement floors. And so now we are going to let our laser beam arrive here in such a way that the lower end of the laser beam hits the carpet before the upper end. So let's see what happens. And it changes direction. So we started out going this way, we're now going that way. The steeper the angle, the bigger the change. Well, we left the material too soon. The other important feature, remember we talked about perpendicular. What if we come on head on? Well, we're going to slow down, but both wheels slow down at the same moment, which means we don't change direction. So let's see how that works. That works pretty well. So our theory of speed change looks like a good one. That speed, you say, well, wait, speed change, isn't the speed of light constant? It's constant in a vacuum. If we move into any other transparent material, we go slower. And it turns out each transparent material has a speed that's kind of characteristic. Some materials share their speeds, but mostly we can use it as an identifier. The ratio of how fast we go in a vacuum to how fast we go in the stuff is called the index of refraction of the stuff. That sounds very abstract, but Peter is going to make this very concrete for you.
So concrete, I'm not even going to bother to talk, and I'm going to throw it to Mary.
Okay, the other Peter.
So index of refraction is the reason why we can see clear things in clear things. Don't think this is a gender stereotype. I'm not doing this because I'm about to talk about washing dishes. But you're doing dishes, you've got a clear glass, right? It's clear. You stick it in clear water, and you can still see it. It's definitely still there. And even if there's water in it, can't you still see it? Right? You can even see the level at which the water stops inside of that beaker. All right, and so why is that? Because what's happening is the light is hitting a barrier. It's traveling through the water, and then it has one speed in the water. When it hits the glass, it has another speed. That's, again, index of refraction lets us know what that speed is relative to a vacuum. Then it goes back into water again, right? And so because of those changes, we're able to see that these clear objects are actually there. This is the reason why your legs might look short in a pool, right? This is the reason why if you saw a fish in the corner of a fish tank, you might see two fish. This is because light is bending, all right? And so I can also take a piece of glass and stick it in other clear material, and you should still be able to see it, right? Yes. Not a problem. Right, there it is. There's the glass. Not an issue at all. Why am I even talking about this? This is water. This is corn oil or vegetable oil. It turns out that oil, corn oil and vegetable oil, have an index of refraction that's really, really close to borosilicate glass. You know who makes borosilicate glass? Pyrex, right? They don't do it as much anymore in your casserole dishes, though. But you can still order beakers that have that index of refraction. And when that happens, actually, first let me ask you, why could you still see it then? Didn't I just say the index of refraction was the same? How come you can still see it? Air, right? We have this transition to air. So let's take a good look again.
Yeah, let's go.
So, I'm new to this job, and you might notice some tongs in here, and when we were setting this up, I was like, I can move this really oily piece of glass with tongs, right? Nope, broke it. And then you can't find it anymore. Now you have broken glass in a vat of oil, invisible glass. So that was fun. But you might also be noticing there's a little bit of writing on this, and you guys have good eyes. You guys can probably still see it, just a little bit. You're probably like, yeah, it's totally still there, and Mary, you suck, right? But you didn't notice this one. Now the whole time. Right? So when light hits a barrier and it changes speed, that's when you can see it. But if light doesn't have to change speed, it becomes optically invisible to you. Okay, so one more time. Oh God, it's my favorite thing. All right, so I'm going to turn it over to Pete. I'm going to wipe the oil off my hands.
So borosilicate glass is a little hard to get for most people. So because we like to make sure things are going on, and I understand you kids have these things.
You knew there was something wrong with that water, right? You're looking at it on the screen like, oh yeah, good call. I'm sorry, I can't touch the camera.
These are things, I understand you call them Orbeez? Where I get them from a florist supplier who calls them water jewels, right?
We're like, I'm here my first week, and he's like, yeah, we've got hydrogel, and I'm like, oh, I got kids.
You mean Orbeez? Like, yeah, we got lots of those. So, these are mostly water, right? When you buy them brand new, they look like little beads, and you put them in water, and they can expand to about 200 times their original size. At which point they have so much water in them that they nearly disappear, right? Depending on how high quality you have, you can get ones that completely disappear, right? The other two things that hydrogel is particularly well known for is it is the stuff that they make disposable contact lenses out of. It is also the stuff that absorbs all the water in a diaper because it can absorb that much water and expand out.
What to do with your own contact lens?
Exactly.
So, up till now, we have dealt with light as a ray. And the word ray is not very descriptive. It just means that it's something that goes from here to there along a straight line. We never really talked about what it might be. And there was a great debate around the time, the 1600s and 1700s, as to what light was. Was there a model? Could we come up with, was it like anything else that we were familiar with? Isaac Newton felt that light was a particle, that it was a little pellet flying through space. A number of other scientists proposed that it was a wave. We really haven't defined wave. We've used the word a little bit, but we have not defined it. And so that's what we would like to do now, because we're going to have a look at what is light. And clearly, if we're going to say light is either a wave or a particle, the first thing we want to do as scientists is find a difference in behavior between waves and particles, and then go look to see what light does. In other words, a scientific statement isn't necessarily true, but it is necessarily falsifiable. If the statement you make can't be proven either true or false, it's not scientific. Okay, but if it's a testable statement, then bingo, we can do science with it. And so how would we test the statement that light is a wave or light is a particle? Well, one of the reasons that you came here is that the University of Pennsylvania has a machine shop and a budget. And so they could make a device to demonstrate wave behavior. And this device has these rods balanced along this line, each connected to a thick piece of steel wire. And so if this was a sheet of plywood and I picked it up, each row of molecules would be connected to the adjacent row by strong molecular forces. And if I picked up that sheet of plywood and wiggled it, the whole sheet would wiggle simultaneously. But here we have a very loose connection between each row of molecules. It's just this skinny piece of steel wire that takes a little bit of time to tell the next guy down the line what to do. And the outcome of that is that. And in fact, that's not just accidental to our wave machine. That's what happens when you have a wave. When water creates a wave, water is not well connected to the water next to it. And it takes a little time for it to tell the next piece of water what to do. And so we see ripples moving through the water. And so here we just have something we would call a pulse. A pulse has a height that we call an amplitude, and it's got a speed. But the thing that we can really do that's interesting is we can start to get periodic motion. Because it takes a repeatable amount of time for this thing to do something. Now you're looking at the whole thing, so it's hard for me to get you to concentrate on the essence of the wave behavior. So on the end of these things, we've got glowing material, and if we light it up, we can just let you see the wave. And if we do that, we can now tell you that the distance between any two identical parts of the wave is called a wavelength. The time it takes for the wave to pass is called a period. The number of waves that happen every second is called a frequency. And it turns out that, and here we have something called a standing wave, because the other thing that waves do is they reflect. And so let's quiet this guy down and send a pulse down there and note what happens. There goes the pulse, bloop, and here comes the pulse. It reflected back. Okay? And so in a standing wave, the waves are coming back and forth and running into each other and creating what looks like a stationary pattern. So, it turns out that, we can bring the lights up again. It turns out that objects reflect. Hockey pucks, basketballs, okay, billiard balls. If we fire them into an object, we know that they bounce off and come back. And so this is not a defining behavior. The same thing would happen if I threw a tennis ball at the wall. Not going to answer the question, is light a wave or a particle that way? However, we could find out what happens when two of these guys come together. So I can send a wave down here, get the reflection coming back, and send another pulse down here and crash them together. Like wave demolition derby. Okay? The excitement builds, huh? All right, so here we go. Here's a wave. Here's another one. Here they go. Nothing. They just kind of went through one another. Let's do that again. Positive pulse. Positive pulse, positive boom, and now they just come. It's like it's not even there. So is that a way to differentiate? Well, what would particles do if I sent two particles together? I mean, I guess we really should do this observation, right? This is science, and we don't want you to just believe what I say. So I'm a particle if only I had another particle. Well, here's a particle. We're coming together, and we don't pass through one another. We didn't go to the other end. So there's a real difference here, okay? This behavior is unique to waves, and it's called superposition. It's got two properties. Property one is that when these things come together, they don't influence each other, and they keep going. It's a pain in the ass if you're a teacher, because sound is a wave. You're out there talking to your friend about what you're doing this weekend, and I'm trying to tell you about waves. It would be really neat if waves were particles. I could shoot down your conversation. I could say, well, like wavelength is coming out here. Here comes your thing. What are you doing this weekend? Okay, no, it doesn't work that way. Your waves pass right through my waves. Your friend gets to choose whether you're more interesting than I am. Annoying. Really annoying. The other thing that happens is when they overlap, and that's a really interesting question, what happens when they both need to change the material? And it turns out that the change adds. And so if I send a positive pulse and another positive pulse, right in the middle we get a double pulse, which is interesting but not terribly surprising. But what if I send a positive pulse and a negative pulse, and there's a moment when they cross when there's nothing? So this is called interference. And in a physics book, the word interference is used for both cases. And we talk about constructive interference if the two guys add, and destructive interference if it's a plus and a minus that combine to give us a zero. And that zero effect is really surprising. Okay? So this is one of the things that we can really use to check on whether something is a wave or a particle. Because if we can get them to pass through one another, so we verified that sound seems to be a wave, that I can't crash into your sound and stop it. But the other question is, can we get it to interfere? One other point before we move these gadgets. This is called a transverse wave because the material involved is wiggling at right angles to the path of the disturbance. So we're sending a disturbance left to right. We're asking each particle to move up and down. There's another wave we could have in which the disturbance is left and right and the propagation is also left and right. This is a push-pull wave, a compression wave, a sound wave. So we've got both possibilities, and it turns out that almost all of the same terminology applies. It's going to repeat, it's got a period, a wavelength, an amplitude, a speed. And so now we've got an image of waves. These are, of course, mechanical waves. We're now going to have a look at a couple of other ones.
Yeah. Sound is a compression wave, right? Because nothing is actually traveling all the way from me to you when you hear this. The sounds in my mouth are just bouncing against the sounds right in front of my mouth. Not yet. Not yet. I'm doing a thing here.
Okay.
Hold on.
Oh, you're right.
Thank you. Nothing went from me to Bill when I chastised him just now. The noise just wiggled next to my mouth, which were the air next to that, and so on and so forth. To show the difference between these kinds of behaviors, we have a neat little device here. This is a ringer. It's an old school bell. We stole it from a school, right? If I press this button, everyone can hear that, right? And you can see that spark that happens right at the top of the coil. That is what makes that hammer move. That is moving because of this little spark up there, right? So you can all see this bell. Most of you can probably hear that bell as well. So the sound waves are going to be the light waves are going to be. If I wanted to block the light waves, that'd be easy. That's done, right? Most of you can't see it now because my hand is opaque and you can't see it. Blocking the sound's a little bit harder, right? But there are ways to block the sound. So this bell, which you may have noticed is mounted in a jar, is also very cleverly a bell jar. So we can take all of the air out of this jar while the bell is running with this roughing pump. So it's going to make a little bit of noise. The pump's a little bit loud when it's going, right? But the bell is ringing. If we start to remove the air, so it's making a very silly noise as the air is coming out. But you can notice that silly noise is changing a little bit. The bell is also changing. You might also notice that that spark is getting bigger and bigger. It turns out sparks are a lot easier to create if there's less air, right? The closer you are to a vacuum, the easier it is to make sparks. It's part of the reason lightning can happen so easily in the upper atmosphere. So you can see that spark is getting really big. And the pump is starting to make almost no noise. So if I turn this off, we all listen for a second. Now some of you may be able to hear a noise, right? But unfortunately, that's because the bell is still attached to the lid, right? So you might be hearing the lid shake a little bit. But that's a kind of a dull thud, kind of drum noise, and not that high, tinny bell noise that we heard, right? So if we listen to this, we can't hear that bell anymore. Now maybe I've done some kind of chicanery, hang by this, and so with all good science, this is reversible. So I can let air back into the jar. And as soon as the air gets back into the jar in the jar can now shake the jar, which shakes the air outside of the jar, which gets to your ears. So it's very easy to see this difference. That's not right now. That's right. It's very easy to see this difference between light waves and sound waves. We can talk about what interference between sound would be. So that's a little kind of esoteric of an idea, right? Because we're used to sounds interacting all the time. I'm talking, you're talking, that's the thing, it's all going, right? So to do science about it, we need to be able to isolate those sounds. So this is a device known as an acoustic interferometer, meaning a way that you measure how sound is interacting. So what we have here, this is a thing called a function generator. Right, this on. And you plugged in. So that's a thing called an oscilloscope, meaning thing that measures waviness. Right, oscilloscope. Here in the center we have a speaker. Right. So we have a speaker here in the center of the device. And we have that going into this tube, right? That yellow line you see on the screen is the signal that is going into that speaker, right? So that's the frequency that is being produced. That noise, that sound, is going into the tube. It splits. Some of the sound goes this way and comes out this hole. Some of the sound goes this way and comes out this hole. And you can hear it. But if we change the device a little bit, we can hear that volume change, right? Nothing has happened to the speaker. The yellow line has not changed. The only thing that has changed is the distance one of those two sounds traveled. So right now, if I tune this in, we can get to a very loud sound. And if I tune it a little more, it gets very quiet. So quiet, I would dare say silent. Of course, now you're going, that's not something I can still hear, right? So, we have figured that out. So we have here another microphone that if we are wired backwards. And when you wire a microphone backwards, it becomes a speaker. So this is a microphone that I'm now going to place right here. So that blue line is what you were hearing. And if I tune this, we can notice I can get very loud and the signal gets very big. And I can tune it out, and it goes to silent. This is interference in sound waves, right? Exactly the same as you saw before in the wave machine. If you have a wave coming, and another wave coming, and they're both going up, right? You have a +1 and a +1, and they run into each other. It becomes a +2. But if you have a +1 and a -1 that run into each other, they become a 0. So what we are doing here, by changing the length of the path, we are changing whether a plus meets with a plus or a plus meets with a minus, right? If you have ever experienced actual proper noise canceling technology, right? There are a lot of things you can buy that say noise canceling, and what they mean is earplugs, like it's just a big pad that makes things silent. But the really expensive ones, right? What they're actually doing is they are hearing a sound and playing it back to you half a wavelength off from how it heard it. So the positive from the outside noise meets the negative from your speakers, and you can't hear it anymore. We've actually gotten this technology to work so well, they have tried installing it at professional sports games. So the people on the field can't hear the the audience at all. And we got that technology to work. It worked amazingly well. So well that they had to remove it because athletes couldn't hear people cheering for them, and so they don't run as fast. This is fine and dandy, right? We can hear it at one point. But wouldn't it be nice if we could see these waves as they're going, right? If we could see these high pressures and low pressures as they're going through? We could do something like, if we put pressure gauges along the edges, right? We could see the high pressure and low pressure as they're moving. But that'd be really hard to see, and it would take time. So we could just let the gas come out. As long as we put more gas in, gas would come out proportional to how much pressure there was. But gas is really hard to see. But if we lit that gas on fire as it was coming out of the tube, we could probably see the high pressure and the low pressure in the standing waves. You have your mark? It should be lower than that. Just lower. So this is what's called a Rubens tube. Named for Mr. Rubens, not the guy who made the sandwich. But what this is we have a speaker at one end of a tube. We have filled that tube with a flammable gas. So that as we pump sound into this tube, those sound waves will travel down, hit the other end of the tube, and come back. And if we pick a sound wave well, we can start to see these standing wave patterns. Right? With the so right now, we're at 310, right, which is what, a little off of D, I think? So we have a sound wave coming down. It's hitting the other end and bouncing back. And by picking that sound wave well, when two ups hit each other, we get a little bit higher pressure. And when two downs hit each other, we get lower pressure. And we get this shape. Right? If instead we went to a different frequency, right? So at this frequency, we can see we still have a standing wave, but we have a different shape, right? A high pressure meets a high pressure here, a low pressure meets a low pressure here. And we get higher flames and lower flames at those points. Previous frequency, there were 4 humps. There are now 3 humps because we're at 3/4 that frequency. If instead we go to a different frequency, we can now see we have the pattern again, but it's now a different pattern, right? So this frequency that I just picked is actually 4/3 the previous frequencies. So instead of 3 humps, we have 4 humps, right? And we have this high pressure and low pressure as they go back and forth. Now, to kind of show this evolution, right, instead of just doing 2 frequencies, we can do this, where we are now going to run through a series of frequencies, and you'll be able to see how it kind of jumps in and out of being in resonance, where it picks these tones that it likes. Wouldn't it be nice if we could listen to something a little better than that? Well, it turns out we have tried a lot of things on this Rubens Tube, and bassoon music is kind of nice on it, but bassoon music tends to be a bit on the boring side. but we have found something that works really well on it. What's really interesting about this, why does Adele look so good in a Rubens Tube? The reason is actually the same reason she sounds so good to you. The human ear has developed such that a sine wave, the mathematically perfect sine wave, is what sounds pretty to us. And it turns out Adele's voice produces such a nice sine wave that even the Rubens Tube can hear it and will produce that standing wave in there. Just to prove that it is not quite a...